Now let's have now a look at what projections are. All right, so let's see. The projection of a vector u on another vector v. Well, you're familiar with projectors and with movies and so on, right? So that's what we're going to be using. So let's say we have a vector u and a vector v. What we want to do is we want to project u on v. That is, we want to see what shadow u makes on v if a light perpendicular to v shines on u. Okay, so we're going to construct a segment which is perpendicular to v, and we're going to be looking at the vector, the shadow, pretty much the shadow vector that u forms on v, and we're going to call this thing the projection of u on v. Notice the notation there. So the v is down as a subscript to indicate that we're projecting on v and we're projecting u. Now, fine and dandy, it's a geometric thing, and we can certainly play with it, and there is a right triangle in there, and so on and so on. We could use a lot of trigonometry, but we're going to stay away from it. We're going to construct a whole bunch of things without actually touching trigonometry. Well, not quite. We're going to have to use trigonometry to construct the things that we want to construct, but once we do, the trigonometry will be out of the picture. So how are we going to do that? Well, let's think about it. How do I figure out what this vector, the projection of u on v is? Well, I know that this vector has the same direction as v, so I'll have to first of all find out what is the unit vector along v, and then I'm going to have to multiply that by the actual length of this projection. So I have to figure out two things now. What is the unit vector of v? Remember, now we're going to identify directions with unit vectors. And I'm going to have to figure out how long that projection is. Both of these things are very simple. We've seen before that the unit vector is obtained by simply taking the vector and dividing it by its length. Okay, so that's fine and dandy. And how about the length of the projection? Well, here is where the little bit of intermediate trigonometry comes in. If theta is the angle between u and v, then we know from trigonometry that that length is going to be equal to the length of u times the cosine of theta. It's the adjacent side. Alright, so that's a first way of figuring out what this vector is all about. But again, notice it has a cosine of theta. We want to get rid of it. Remember, I just told you before that the cosine of theta actually has a formula in terms of dot products and norms and lengths. So we're going to be using that one. So that means that we have the vector v divided by its norm that gives us the unit vector. Then the length of u is still there, and then cosine of theta is u dot v divided by length of u times length of v. Now notice that we can cancel the two u's, and we end up with simply v, the vector v, which gives us the direction. Then u dot v stays there, and then we have two lengths of v in the denominator, and then multiply together to make a length of v squared. And notice that this time it's a fairly simple formula, and it's a formula that does not involve any trigonometry explicitly. Okay? Notice also that in this formula the v represents, the v on the left hand side represents the vector, which gives us the direction, and the fraction that follows it, and of course you can put that fraction before the vector if you prefer, is a scalar. If you think about it, u dot v is a scalar. It's a sum of products, right? So it's going to be just a number. And of course the length of the vector squared is also a scalar, so the whole thing is a scalar. So we're just using a scalar multiple of v. There are a few more concepts related to the idea of a projection. First of all, we are going to use later on the idea of a scalar projection of u on v. What is that? Well, very simple. It's just the length of the projection. Okay, so the projection is a vector. The scalar projection is its length. Okay, so if we use the formula that we have just found out for the formula for the projection, and we take its length, and then we remember properties of the scalar multiplication of a scalar times a vector with respect to the length, we find out that this is equal to the length of v times the absolute value of u dot v divided by the length of v squared, which is already a positive number. Now we're dealing with all we're dealing with is numbers, and of course we can cancel that length of v with the length of v in the denominator, and it turns out to be just the absolute value of u dot v divided by the length of v. So it's just a fairly simple concept there. The other concept that we may be using, that we will be using later on, is the idea of the component of U orthogonal to V. Now remember, orthogonal, I haven't defined it really, probably you have seen that, you have heard that word before, but orthogonal and perpendicular are pretty much used interchangeably as long as we're dealing with geometric vectors. Later on, we're going to make a little distinction between the two. So what is the component of U orthogonal to V? Okay, what we're looking at is we're trying to look at this new green arrow. So the one that goes from the projection, from the tip of the projection to the tip of the vector U. Now, think about that vector as the vector W, and notice that if I take W and I add to it the projection of U on V, I've got the sum of those two sides of the triangle. But the triangle rule, that sum is equal to the vector U itself. And therefore, that means that this component of U orthogonal to V is just given by the vector U itself minus its projection. Okay? So again, it's a little number crunching, not a lot to do with it for now, but it will come in handy later on for some applications. So just keep it in mind for now, play with it, compute it a few times just to get familiar with it.